Good evening, and welcome back to Boring Science for Sleep. Tonight, we're going to take a quiet journey to one of the strangest objects in the universe, a place where matter becomes so dense that the familiar rules of everyday life seem to dissolve into something far more mysterious. Before we begin, take a moment to settle in. Let your shoulders relax. Let your breathing slow. And if you feel like it, leave a comment below telling us where you're watching from tonight and what time it is where you are. It's always peaceful to see listeners from different parts of the world drifting into sleep beneath the same stars. Now, let's begin our journey. Far out in space, scattered among the countless stars of our galaxy, there exist objects that are both incredibly small and unimaginably heavy. These objects are called neutron stars, and they are born from the death of something much larger. Imagine a star far more massive than our Sunday. For millions of years it burns brightly, balancing the crushing force of gravity with the outward pressure of nuclear fusion deep inside its core. But one day, that balance begins to fail. The star runs out of fuel, the pressure that once pushed outward fades, and gravity, the quiet sculptor of the cosmos, suddenly takes control. In only a fraction of a second, the star's core collapses inward. Matter falls toward the center at astonishing speed. Atoms themselves are crushed together. Electrons and protons merge, and the core of the star is compressed into something almost unimaginable. What remains is no longer a normal star. Instead, it becomes an object about the size of a city, perhaps only 20 kilometers across. Yet inside that tiny sphere lies more mass than our entire Sunday. A whole star compressed into something no larger than a small metropolitan area. This is a neutron star, a place where gravity is so strong that the surface is curved in ways that bend space and time. A place where matter is squeezed so tightly that the familiar structure of atoms can no longer exist. Instead of atoms, the star becomes a vast ocean of neutrons packed together with unimaginable density. To give you a sense of just how dense this object is, imagine something very simple. Imagine holding a small spoon. Now imagine that spoon scooping up a tiny sample of material from the surface of a neutron star. Just one spoonful. That small amount of matter would weigh billions of tons, more than entire mountains, more than the weight of great ships or towering buildings, all compressed into a single spoonful. These strange objects are scattered throughout the Milky Way, quiet remnants of stars that once shone brightly in the sky. Some spin incredibly fast, rotating hundreds of times each second. Others possess magnetic fields so powerful they could erase data from a computer thousands of kilometers away. Some drift alone through the galaxy. Others dance in pairs, orbiting each other in silent cosmic spirals. And every one of them is a reminder of how extreme the universe can become. Tonight, we'll slowly explore 100 fascinating facts about neutron stars. We'll travel through the life and death of massive stars. We'll learn how matter can be crushed into unimaginable densities. We'll discover pulsars, magnetars, and collisions that create some of the most powerful explosions in the universe. But we'll explore these ideas slowly, calmly, like a quiet journey through the night sky. So as you listen, allow your thoughts to drift gently among the stars. Imagine distant suns collapsing into tiny spheres of unimaginable gravity, and let the strange, quiet physics of neutron stars guide you softly towards sleep. Long before a neutron star is born, there must first be a star. Not just any star, but a massive one, far larger than our Sunday. Stars like this begin their lives quietly. Vast clouds of gas drift through space, slowly collapsing under the pull of gravity. As the cloud compresses, the center becomes hotter and denser until eventually nuclear fusion ignites. a new star is born. For millions of years, this star burns brilliantly. Deep within its core, hydrogen atoms collide and fuse together, forming helium and releasing enormous amounts of energy. That energy pushes outward. Gravity pulls inward. And for most of the star's life, those two forces exist in delicate balance. This balance is what allows a star to shine steadily in the night sky. But even stars cannot burn forever. A massive star consumes its fuel much faster than a smaller star like our Sun. The larger the star, the more violently fusion occurs inside its core. It's a bit like a very large campfire. It burns brighter, hotter, but it also burns through its wood much more quickly. Over time, the star begins to exhaust the hydrogen at its center. When this happens, the star must find new ways to keep producing energy. The core begins fusing heavier elements. Hydrogen becomes helium. Helium fuses into carbon. Carbon into oxygen. Then neon. Then silicon. Each stage of fusion produces heavier elements and requires even higher temperatures. Inside the core, the pressure becomes enormous. Temperatures climb to millions, then hundreds of millions, then billions of degrees. The star becomes a kind of cosmic furnace. But there is a limit to how far this process can go. Eventually, the star begins producing iron in its core. And iron is a problem. Unlike lighter elements, iron cannot release energy through fusion. When iron forms, the star's nuclear furnace begins to stall. Fusion reactions slow down. The outward pressure that once held gravity in check begins to weaken. And gravity, patient and relentless, begins to win. The core of the star becomes unstable. Without the outward push of fusion, nothing remains strong enough to support the immense weight of the layers above. What happens next occurs incredibly fast. In less than a second, the core collapses inward. Imagine the mass of an entire star rushing toward its center. Matter accelerates at tremendous speed. The core shrinks rapidly, compressing smaller and smaller. Atoms are squeezed together. Electrons are forced into protons. And when those particles combine, they form neutrons. In this violent moment, the entire core transforms into an incredibly dense sphere of neutron-rich matter. This collapsing core will soon become a neutron star. But the story is not finished yet, because the outer layers of the star are still falling inward. When the collapsing material crashes into the newly compressed core, something extraordinary happens. The dense neutron core suddenly resists further compression. It behaves almost like an impossibly rigid surface. The infalling material slams into it at tremendous speed. The energy of this collision is so enormous that it reverses the collapse. A shockwave bursts outward through the star, and in a matter of moments, the star explodes. This explosion is known as a supernova. A supernova is one of the most powerful events in the universe. For a short time, the exploding star may shine brighter than an entire galaxy. The outer layers of the star are blasted into space at thousands of kilometers per second. Gas and dust expand outward in glowing clouds. These expanding remnants will drift through the galaxy for thousands of years. Within them are elements forged inside the star's core: carbon, oxygen, silicon, iron, and many others. These materials will eventually mix with interstellar clouds. From those clouds, new stars and planets will form. Even the atoms in our own bodies were once part of stars that exploded long ago. In this sense, supernovae are not only endings, they are also beginnings. At the center of the explosion, the collapsed core remains. The rest of the star has been blasted away. But this tiny, ultra-dense object survives. All the mass of the star's core has been compressed into a sphere perhaps only 20 kilometers across. A city-sized object containing more mass than the Sun. This is the birth of a neutron star. For a moment after the explosion, the newborn neutron star is incredibly hot. Temperatures inside it may reach trillions of degrees. Neutrinos, tiny ghost-like particles, pour outward in vast numbers. The surrounding space fills with radiation and expanding clouds of gas. Slowly, the chaos of the explosion fades. The expanding nebula drifts farther away, and at the center, the neutron star remains. A silent remnant of a once mighty star, small, dense, and governed by some of the most extreme physics anywhere in the cosmos. In the next part of our journey, we will explore what happens inside that tiny sphere of collapsed matter, how protons and electrons merge to form neutrons, how gravity compresses matter into something denser than anything we can imagine on Earth, and how a neutron star born from the death of a massive star becomes one of the most extraordinary objects in the universe. After the tremendous explosion of a supernova, what remains at the center of the shattered star is something both incredibly small and unimaginably dense. A newborn neutron star. It may be difficult to imagine how such an object forms, because the physics involved pushes far beyond anything we experience in everyday life. Inside the collapsing core of a massive star, matter is squeezed under pressures so extreme that the familiar structure of atoms begins to break down. To understand this transformation, it helps to remember what ordinary matter is made of. Every atom contains a tiny nucleus composed of protons and neutrons, surrounded by a cloud of electrons. In normal environments like the air we breathe or the ground beneath our feet, these particles exist comfortably separated from one another. But inside the collapsing core of a dying star, the situation becomes very different. Gravity compresses the material of the core with unimaginable force. Layers of stellar matter fall inward at incredible speed. The pressure increases rapidly, rising to levels billions of times greater than anything found on Earth. Atoms are forced closer and closer together. Eventually, the space between them disappears entirely. Electrons, which normally orbit the nucleus at a comfortable distance, are pushed inward toward the protons inside atomic nuclei. When the pressure becomes high enough, something remarkable happens. Electrons and protons combine. Through a process known as electron capture, a proton absorbs an electron and transforms into a neutron. This reaction releases a tiny particle called a neutrino, which escapes the star at nearly the speed of light. As the collapse continues, more and more protons capture electrons, creating vast numbers of neutrons. Gradually, the core of the star becomes a dense sea of neutrons packed tightly together. The familiar atoms that once existed there are gone. What remains is a new form of matter, neutron degenerate matter. The speed of this transformation is astonishing. The collapse of the stellar core happens in less than a second. Within that brief moment, a region that once spanned thousands of kilometers shrinks dramatically. Gravity squeezes the core into a sphere only about 20 kilometers across. That is roughly the size of a small city. Imagine compressing the mass of an entire star's core, something heavier than our sun, into an object no larger than a city skyline. This is the birth of a neutron star. Because the mass is packed into such a tiny volume, the density becomes almost impossible to comprehend. A single cubic centimeter of neutron star material could weigh hundreds of millions of tons. Even a tiny sample of its surface matter would be incredibly heavy. As mentioned earlier, a simple spoonful of neutron star material might weigh billions of tons. Of course, removing such a sample is purely hypothetical. The gravity of the neutron star would make that nearly impossible. But the comparison helps us grasp just how dense this object truly is. Gravity on the surface of a neutron star is incredibly strong. If you were somehow able to stand on its surface, which would be impossible for many reasons, you would feel gravity hundreds of billions of times stronger than the gravity on Earth. A human body would not survive such conditions. Even mountains could not exist there. Any structure larger than a few centimeters would be crushed by the immense gravitational pressure. As a result, the surface of a neutron star is thought to be extremely smooth compared to planets like Earth. Some scientists have estimated that the tallest mountains on a neutron star might be only a few millimeters high. Anything larger would collapse under its own weight. Despite its incredible density, the neutron star is not completely solid in the way we normally think of solid objects. Its outermost layer forms a thin crust of extremely dense atomic nuclei arranged in a rigid lattice. Beneath this crust lies an ocean of neutrons packed tightly together. In this strange environment, neutrons may behave like a superfluid, a form of matter that flows without friction. The physics inside a neutron star is so extreme that scientists continue to study it as a natural laboratory for understanding matter under extraordinary conditions. Some theories even suggest that deeper inside the star, the particles themselves may begin to break apart into their fundamental components, quarks. If this is true, the center of a neutron star could contain exotic forms of matter that cannot exist anywhere else in the universe. Another remarkable feature of neutron stars is how fast they can spin. When the core of the star collapses, its rotation speeds up dramatically. This happens because of a principle known as conservation of angular momentum. It is similar to what happens when a spinning ice skater pulls in their arms. As the radius becomes smaller, the rotation becomes faster. In the case of a collapsing star, the effect is extreme. A star that once rotated slowly may suddenly begin spinning dozens, hundreds, or even hundreds of times per second. The result is a neutron star that rotates incredibly quickly, carrying immense energy in its motion. Some of these rapidly spinning neutron stars will later become objects known as pulsars, emitting beams of radiation that sweep across space like cosmic lighthouses. But we will explore pulsars in more detail later. At the moment of its birth, a neutron star is also incredibly hot. Temperatures inside the star can reach trillions of degrees during the collapse. However, the newborn neutron star cools rapidly. One of the primary reasons for this cooling is the enormous number of neutrinos released during the formation process. Neutrinos interact very weakly with matter, allowing them to escape the star easily. As they stream outward into space, they carry away enormous amounts of energy. In fact, most of the energy released during a supernova is emitted not as light, but as neutrinos. Within a few minutes, the newborn neutron star begins to settle into a quieter state. Its temperature gradually drops, its rotation stabilizes, and the violent chaos of the supernova fades into silence. What remains is one of the most extraordinary objects in the universe. A star compressed into a sphere only tens of kilometers across. An object with gravity strong enough to bend space and time around it. A place where matter exists in forms unlike anything we encounter on Earth. Yet neutron stars are not rare. Astronomers estimate that there may be hundreds of millions of them scattered throughout our galaxy. Most are invisible to ordinary telescopes. They drift quietly through the darkness, remnants of stars that exploded long ago. Silent cosmic cities of gravity. In the next part of our journey, we will explore just how powerful the gravity of a neutron star truly is. How such a small object can contain the mass of an entire star, and how the incredible density of neutron stars pushes the laws of physics to their limits. Because when matter is compressed to such extreme levels, the universe begins to reveal some of its most fascinating secrets. A neutron star is one of the strangest objects in the universe. Not because it is large. In fact, it is astonishingly small. Compared to most stars, a neutron star is tiny, only about 20 kilometers across, sometimes even less. That is roughly the distance across a medium-sized city. Yet inside that small sphere lies something extraordinary. The mass of an entire star. often greater than the mass of our Sun-day. Trying to imagine this is not easy. The Sun itself is enormous. Its diameter is about 1.4 million kilometers. It contains nearly all the mass in our solar system. Now imagine taking that immense mass and compressing it down until it could fit comfortably inside a city. This is why neutron stars are sometimes described as cities of gravity. Small in size, but holding incredible mass within them. Because the mass is so tightly packed, the density of a neutron star becomes almost impossible to comprehend. On Earth, even the densest materials like lead or uranium still contain atoms with large empty spaces between their nuclei. But inside a neutron star, those spaces have disappeared. The particles are pressed together until they form an almost continuous sea of neutrons. The result is matter that is billions of times denser than anything found on our planet. To help visualize this density, scientists often use a famous comparison. Imagine you could scoop up 1 teaspoon of neutron star material. That tiny spoonful would weigh billions of tons, more than the weight of a mountain, more than the weight of entire skyscrapers or ships, all compressed into a tiny sample no larger than a spoon. Of course, such a sample could never be brought to Earth. Outside the intense gravity of the neutron star, that material would explode outward almost instantly. But the comparison helps illustrate the incredible density hidden inside these objects. This immense density also means that gravity on the surface of a neutron star is extraordinarily strong. If you dropped an object from just 1 meter above the surface, it would hit the ground in a fraction of a second with tremendous force. The gravitational pull of a neutron star can be hundreds of billions of times stronger than Earth's gravity. Even light itself struggles to escape easily from such intense gravity. Not quite as dramatically as with a black hole, but still enough to bend and distort the path of light around the star. This effect is predicted by Einstein's theory of relativity, and neutron stars provide one of the best places in the universe to observe these extreme gravitational effects. Because gravity is so strong, the shape of a neutron star is almost perfectly spherical. Mountains and valleys cannot grow very large. On Earth, mountains can rise several kilometers above the surrounding land. But on a neutron star, gravity crushes any large structures. Even a small bump on the surface would collapse under its own weight. Scientists estimate that the tallest mountains on a neutron star might only reach a few millimeters high. In comparison with the size of the star, its surface is nearly perfectly smooth, almost like a polished sphere floating in space. Another remarkable effect of this extreme gravity is something known as gravitational time dilation. According to Einstein's theory of relativity, time passes more slowly in stronger gravitational fields. Near the surface of a neutron star, gravity is so intense that time itself flows differently. If you could place a clock on the surface of a neutron star, it would tick slightly slower than a clock far away in space. This difference is small but measurable. It reminds us that neutron stars are not only dense objects, they are also places where the fabric of space and time behaves in unusual ways. Because neutron stars are so compact, their gravitational influence is concentrated in a very small region. If our Sun were replaced by a neutron star of the same mass, the orbits of the planets would remain mostly the same. Earth would still circle the neutron star once every year, but the sky would look very different. Instead of a bright glowing star, we would see a small, incredibly dense object no larger than a city. It would emit radiation and intense magnetic energy, but it would not resemble the familiar sun that lights our days. This thought experiment helps illustrate something important. The strength of gravity depends mostly on mass, not size. Even though a neutron star is small, its mass is immense. And that mass creates a powerful gravitational field. Many neutron stars spin incredibly fast. When the star collapsed during the supernova explosion, its rotation sped up dramatically. Imagine a spinning object shrinking while maintaining its angular momentum. As it becomes smaller, its rotation becomes faster. The same thing happens during the collapse of a massive star's core. Some neutron stars spin hundreds of times per second. At these speeds, a point on the surface of the star may move through space at thousands of kilometers per hour. Despite this incredible motion, the star remains stable because its gravity is so strong. Even though neutron stars are tiny compared to ordinary stars, their influence can extend far into space. Their gravity can capture nearby material. Their magnetic fields can accelerate particles to incredible energies. And in some cases, their intense radiation can be detected across vast distances in the galaxy. But perhaps the most fascinating thing about neutron stars is that they exist right at the boundary of what physics allows. They are not black holes, but they are very close to becoming them. If a neutron star gathers too much additional mass, gravity may push it beyond the limits that neutron matter can support. When that happens, the star may collapse further, and the result could be a black hole. For now, though, neutron stars remain balanced between these extremes. Small, dense, powerful, cities of gravity drifting quietly through the galaxy. Remnants of stars that once burned brightly, and laboratories where the universe reveals some of its most extraordinary physics. In the next part of our journey, we will explore the strange layers that make up a neutron star, from its solid crust to the mysterious ocean of neutrons hidden deep within its interior. From a distance, a neutron star may appear simple, a small, dense sphere drifting through the darkness of space. But beneath that quiet exterior lies a structure unlike anything else in the universe. Inside a neutron star, matter is arranged in strange layers created by gravity so intense that the familiar behavior of atoms begins to change. To understand this hidden world, imagine descending slowly toward the surface of a neutron star. At first, what you would encounter is something surprisingly solid: the crust. The crust of a neutron star forms the outermost shell of the object. It is only about 1 kilometer thick, yet even this thin layer contains more mass than many entire mountains on Earth. Despite the extreme gravity, the crust behaves like a rigid solid. But it is not made of normal rock or metal. Instead, it consists of incredibly dense atomic nuclei packed together in a crystalline structure. In this strange environment, atoms are compressed so tightly that their electrons are stripped away. The nuclei themselves are pushed close together, forming a kind of metallic lattice. Imagine a vast crystal made not of ordinary atoms, but of ultra-dense nuclei arranged in repeating patterns. The pressure holding this structure together is enormous. The crust is thought to be one of the strongest materials in the universe. Some scientists estimate that neutron star crust could be billions of times stronger than steel. If a mountain-sized structure existed there, it would resist deformation far better than any material we know on Earth. Yet even this incredibly strong crust cannot remain perfectly stable forever. Neutron stars rotate rapidly. Their intense gravity constantly pulls inward. Magnetic forces twist and strain the surface. Over time, these stresses build up. Eventually, the crust may crack suddenly in what scientists call a starquake. A starquake is similar in concept to an earthquake on Earth, but vastly more powerful. When the crust fractures, enormous amounts of energy are released. The neutron star may briefly change its rotation rate. Astronomers observing pulsars rapidly spinning neutron stars sometimes detect these sudden changes. They appear as tiny jumps in the star's rotation speed, known as glitches. These glitches provide clues about what is happening deep inside the star. Just beneath the crust lies one of the strangest environments in the cosmos, a region where neutrons begin to break free from atomic nuclei. Here, gravity compresses matter so tightly that nuclei can no longer hold all their neutrons together. Some of the neutrons escape, They form a dense fluid that flows between the remaining nuclei. This region is often described as a neutron ocean, but unlike any ocean on Earth, this one behaves according to the laws of quantum physics. Under the extreme conditions inside a neutron star, the free neutrons may form what physicists call a superfluid. A superfluid is a remarkable state of matter in which particles move without friction. In this state, the fluid can flow endlessly without losing energy. It can climb walls, form strange vortices, and behave in ways that seem almost magical compared to normal liquids. On Earth, superfluids can be created in laboratories using extremely cold helium, but inside a neutron star, superfluidity arises not because of low temperatures, but because of immense pressure and density. The neutrons become so tightly packed that quantum effects dominate their behavior. They begin to move together in coordinated patterns, forming a fluid that flows without resistance. This neutron superfluid plays an important role in the behavior of neutron stars. As the star rotates, the superfluid cannot simply spin like a normal liquid. Instead, it forms countless tiny quantized vortices, microscopic whirlpools where the fluid circulates. Each vortex carries a small amount of angular momentum. Together, they allow the superfluid to match the star's overall rotation. When the crust of the neutron star shifts during a starquake, these vortices can suddenly rearrange themselves. This sudden change can transfer angular momentum between the superfluid interior and the crust. Astronomers believe this process is responsible for the mysterious rotational glitches observed in many pulsars. In this way, the strange quantum fluid deep inside the star can influence what we observe from light years away. Deeper still beneath the neutron ocean, matter becomes even more extreme. The atomic nuclei that once formed the crust are gradually crushed apart. Protons and neutrons pack closer and closer together. Eventually, the material becomes an almost pure sea of neutrons. At these depths, gravity squeezes matter into densities far beyond anything that can be recreated in laboratories. Scientists are still trying to understand exactly what happens in this region. Some theories suggest that the neutrons themselves may begin to break down into smaller particles called quarks. If this happens, the core of the neutron star might contain exotic forms of matter, sometimes called quark matter or strange matter. These ideas remain theoretical, but neutron stars provide one of the few places in the universe where such conditions might exist naturally. Despite these extreme conditions, neutron stars are surprisingly stable. The pressure created by the densely packed neutrons pushes outward, resisting the crushing pull of gravity. This balance allows the star to remain intact. But the balance is delicate. If a neutron star gains too much additional mass, for example, by pulling in material from a nearby companion star, gravity may eventually overwhelm the internal pressure. When that happens, the star can collapse again. This time, nothing will stop the collapse. The result may be the formation of a black hole. For now, though, most neutron stars remain stable for millions or even billions of years. They spin quietly through the galaxy. Their solid crusts hold immense pressure. Their interiors contain oceans of superfluid neutrons swirling with quantum motion. They are silent, invisible cities of gravity objects where matter behaves in ways that challenge our understanding of physics. Yet from great distances, astronomers can detect their presence. Some neutron stars emit beams of radiation that sweep across space like lighthouse beams. Others unleash powerful bursts of energy from their magnetic fields. These remarkable objects reveal themselves in many ways. And in the next part of our journey, we will explore one of the most fascinating forms they can take. Rapidly spinning neutron stars known as pulsars, cosmic lighthouses that send rhythmic signals across the galaxy. Some neutron stars live quiet and nearly invisible lives. They drift through space as dense, silent remnants of long-dead stars. but others reveal themselves in a far more dramatic way. They spin rapidly, they emit powerful beams of radiation, and they send rhythmic signals across the galaxy like a cosmic heartbeat. These remarkable objects are known as pulsars. The story of pulsars begins with the birth of a neutron star itself. When the core of a massive star collapses during a supernova, its size shrinks dramatically from thousands of kilometers across to only about 20. But something important is conserved during this collapse. Rotation. Just like a spinning ice skater pulling in their arms, the collapsing star spins faster as it shrinks. What may once have been a slow rotation becomes incredibly rapid. Some neutron stars rotate dozens of times per second. Others spin even faster, hundreds of times each second. One complete rotation can occur in just a few milliseconds. These are some of the fastest rotating objects in the universe. But rotation alone does not create a pulsar. Another key ingredient is the neutron star's magnetic field. When a star collapses into a neutron star, its magnetic field becomes enormously compressed. Imagine taking the magnetic field of an entire star and squeezing it into an object only the size of a city. The result is an incredibly powerful magnetic field trillions of times stronger than Earth's. This magnetic field channels streams of energetic particles away from the star's surface. As these particles accelerate along the magnetic field lines, they emit radiation. This radiation often takes the form of radio waves, though pulsars can also emit X-rays and gamma rays. These emissions do not spread evenly in all directions. Instead, they emerge in narrow beams that shoot outward from the neutron star's magnetic poles. Now imagine a lighthouse standing along a dark coastline. Its bright beam rotates steadily, sweeping across the ocean. Ships see the light only when the beam points toward them. The same thing happens with pulsars. As the neutron star spins, its radiation beams sweep through space. If Earth happens to lie in the path of one of those beams, we detect a brief flash of radio waves each time the beam passes our direction. Because the star rotates regularly, these flashes occur at extremely precise intervals. To our instruments, they appear as repeating pulses, and so the name was born. Pulsar. The discovery of pulsars is one of the most fascinating stories in modern astronomy. In 1967, a graduate student named Jocelyn Bell Burnell was studying signals from a large radio telescope in England. She noticed a strange pattern in the data, a signal that appeared every 1.337 seconds, repeating again and again with perfect regularity. At first, the signal seemed so unusual that some researchers jokingly wondered if it might come from an alien civilization. They even gave the source the nickname LGM-1, short for Little Green Men. But soon, other similar signals were discovered. Astronomers realized they were not hearing messages from extraterrestrial beings. They were detecting the steady pulses of rotating neutron stars. A new class of cosmic objects had been discovered. Pulsars are remarkable not only for their rotation but also for their precision. Some pulsars keep time so accurately that they rival the best atomic clocks on Earth. Their pulses arrive with such regularity that astronomers can predict their timing years in advance. If even the tiniest disturbance occurs, perhaps from a passing gravitational wave or the presence of an orbiting companion star, the timing of the pulses may shift slightly. By studying these tiny variations, scientists can learn a great deal about the pulsar and its surroundings. In fact, pulsars have been used to detect some of the most subtle phenomena in the universe. One particularly interesting type of pulsar is called a millisecond pulsar. These neutron stars spin incredibly fast, sometimes more than 600 rotations per second. Their rapid spin is thought to come from interactions with companion stars. If a neutron star orbits close to another star, it may pull gas from its companion. As this material spirals inward, it transfers angular momentum to the neutron star, spinning it up like a cosmic flywheel. Over time, the neutron star becomes a millisecond pulsar, rotating at astonishing speed. Despite their incredible power, pulsars are surprisingly small. Their entire structure fits within a sphere about the size of a city, yet they contain more mass than the Sun and produce beams of radiation detectable across vast distances. Some pulsars have been observed thousands of light years away. Their rhythmic signals travel through space for centuries before finally reaching Earth. When astronomers point their radio telescopes toward these distant objects, they hear the steady ticking of a neutron star rotating far across the galaxy. It is almost like listening to a distant cosmic clock. Over time, however, pulsars gradually slow down. Each rotation releases a tiny amount of energy into space. As the neutron star radiates energy away, its spin becomes slightly slower. This process can continue for millions of years. Eventually, the pulsar's radiation beams grow weaker and its pulses fade. The star becomes quiet again, another silent neutron star drifting through the galaxy. Yet during their active lifetimes, pulsars serve as extraordinary tools for astronomers. They allow scientists to study gravity, magnetic fields, and the behavior of matter under extreme conditions. Some pulsars exist in binary systems where two neutron stars orbit each other. Their precise timing has helped confirm the existence of gravitational waves, ripples in space-time predicted by Einstein's theory of relativity. In this way, pulsars are not only fascinating objects, they are also powerful instruments for exploring the fundamental laws of physics. Far out in the galaxy, these cosmic lighthouses continue to spin. Their beams sweep across the darkness again and again. Some pulses arrive at Earth after traveling for thousands of years. Tiny signals from distant neutron stars. Steady, precise, endlessly repeating. In the next part of our journey, we will encounter an even more extreme form of neutron star. Objects with magnetic fields so powerful they can distort atoms and unleash bursts of energy capable of affecting entire regions of space. These extraordinary stars are known as magnetars. Among the many strange varieties of neutron stars, there exists an even more extreme kind. Objects so powerful that their magnetic fields stretch the limits of physics itself. These extraordinary stars are known as magnetars. If ordinary neutron stars are already among the most intense objects in the universe, magnetars take those extremes and push them even further. Their magnetic fields are the strongest known anywhere in the cosmos. So strong that they can reshape matter, twist space around them, and release bursts of energy powerful enough to be detected across the galaxy. To understand just how intense a magnetar's magnetic field is, it helps to start with something familiar. The magnetic field of Earth protects our planet from charged particles streaming from the sunday. It guides compasses and shapes the glowing curtains of the aurora near the poles. Yet, Earth's magnetic field is actually quite weak. Even a simple refrigerator magnet is stronger. Now imagine a neutron star. When a massive star collapses during a supernova, its magnetic field becomes compressed along with the rest of the star's matter. The field lines that once stretched across millions of kilometers are squeezed into a sphere only about 20 kilometers wide. As a result, the magnetic field becomes enormously stronger. In a typical neutron star, the magnetic field may already be trillions of times stronger than Earth's. But in a magnetar, the field becomes even more extreme. A magnetar's magnetic field can reach strengths 1,000 times stronger than that of ordinary neutron stars. These fields are so intense that if a magnetar passed halfway between the Earth and the Moon, its magnetic field could erase the data from every credit card on our planet. Closer than that, the effects would become far more dramatic. The magnetic forces could begin to distort atoms themselves. Under such intense magnetic fields, matter behaves in unfamiliar ways. Atoms become stretched and elongated. Electrons spiral tightly around magnetic field lines. The very structure of matter can begin to change. The magnetar becomes not only a powerful star, but also a natural laboratory where physics operates under conditions that cannot be recreated on Earth. But these extreme magnetic fields also place enormous stress on the magnetar itself. The magnetic forces twisting through the star's interior constantly pull and strain the crust. Over time, this pressure can build to incredible levels. Eventually, the crust of the magnetar can no longer withstand the stress. And when that happens, the star experiences something called a starquake. A starquake is similar in concept to an earthquake on Earth, but instead of tectonic plates shifting across a planet's surface, it is the solid crust of a neutron star suddenly cracking under the strain of magnetic forces. When the crust fractures, the magnetar's magnetic field rearranges itself violently. Huge amounts of energy are released. This sudden release of energy travels outward into space in the form of radiation. Astronomers observe these events as brief but powerful bursts of high-energy light. These bursts are known as magnetar flares. Magnetar flares are among the most energetic events in the universe. For a brief moment, sometimes only a fraction of a second, the magnetar can release more energy than our sun produces in hundreds of thousands of years. The energy radiates outward in powerful waves of gamma rays and X-rays. If such an event occurred too close to Earth, it could potentially affect our planet's atmosphere. Fortunately, the known magnetars are located safely far away. But even at great distances, their flares can be detected by space telescopes. These flashes of radiation travel across thousands of light years before reaching our instruments. When scientists analyze these signals, they are witnessing the violent rearrangement of a magnetar's magnetic field. One famous magnetar flare occurred in December 2004. It came from a magnetar located about 50,000 light-years away, in a neighboring region of the Milky Way. Even at that enormous distance, the flare briefly affected Earth's atmosphere. It was the brightest burst of gamma rays ever recorded from outside our solar system. In just a fraction of a second, the magnetar released more energy than the sun produces in over 100,000 years. For a moment, detectors across the solar system were overwhelmed by the intensity of the radiation. And yet the source of that immense energy was something only about 20 kilometers across. Magnetars also tend to rotate more slowly than many pulsars. While some pulsars spin hundreds of times per second, magnetars often rotate only once every few seconds. This slower rotation may be connected to their powerful magnetic fields. The intense magnetism gradually drains energy from the star's rotation, causing it to slow down over time. But even though magnetars spin more slowly, their magnetic energy makes them incredibly dynamic objects. Their crusts may crack repeatedly, their magnetic fields twist and reconnect, and their flares can erupt suddenly without warning. Despite their dramatic behavior, magnetars are relatively rare. Astronomers currently know of only a few dozen confirmed magnetars in our galaxy. But scientists suspect that many more may exist, quietly hidden among the population of neutron stars. Some may have already passed through their most active phase. Others may be waiting silently for their next magnetic eruption. Each magnetar offers scientists a glimpse into one of the most extreme environments in the universe. A place where gravity, magnetism, and quantum physics combine in extraordinary ways. Far across the galaxy, these strange stars continue their quiet lives. Their magnetic fields stretch invisibly through space. Occasionally, a starquake shatters their crust. A brilliant flare flashes outward across the cosmos, and then the magnetar grows silent once more. A tiny, powerful remnant of a long-dead star. In the next part of our journey, we will explore what happens when neutron stars do not exist alone. Some neutron stars orbit each other in close pairs, spiraling slowly together through space. When two of these dense objects collide, the result is one of the most spectacular events in the universe, a cosmic merger that can shake space-time itself and create some of the heaviest elements known to exist. Most neutron stars travel alone. They are the quiet remnants of massive stars that once exploded long ago, drifting silently through the galaxy. But sometimes, the universe arranges something even more fascinating. Two neutron stars can become locked together in a gravitational dance. These systems are known as binary neutron stars. Two incredibly dense objects, each containing more mass than the Sun, orbiting each other across the darkness of space. From a distance, the motion might appear graceful and calm, but the physics involved is among the most extreme anywhere in the cosmos. To understand how such a pair can form, we must return once again to the life of massive stars. Many stars in the universe are not solitary. They are born in binary systems where two stars orbit each other from the very beginning. If both of these stars are massive enough, each may eventually explode as a supernova. After the first star collapses into a neutron star, the system may remain intact. Later, when the second star reaches the end of its life, it too collapses into a neutron star. If the explosion does not tear the system apart, the result is something remarkable. Two neutron stars orbiting each other, each only about 20 kilometers across, yet together containing more mass than two suns. At first, their orbit may be relatively wide. They circle each other at a safe distance, completing each orbit in hours or days. But the universe has a subtle way of changing their motion over time. According to Einstein's theory of general relativity, accelerating massive objects create ripples in space-time known as gravitational waves. These waves travel outward at the speed of light, carrying energy away from the system. As the binary neutron stars orbit one another, they constantly emit gravitational waves. Very slowly, the system loses energy. And as energy escapes, the orbit begins to shrink. The two stars spiral closer together. This spiraling motion can continue for millions or even billions of years. Each orbit becomes slightly smaller than the last. The neutron stars move faster and faster as their distance decreases. Eventually, the system enters its final phase. The stars circle each other hundreds of times per second. Their orbital speeds reach a significant fraction of the speed of light. The gravitational waves they emit become stronger and stronger, and the spiral inward accelerates rapidly. In the final seconds before the collision, the stars whirl around each other in an incredible cosmic dance. Two city-sized objects moving at extraordinary speeds. Gravity pulling them together. Space-time itself trembling with their motion. Then, finally, the two neutron stars collide. This moment is known as a neutron star merger. The impact releases an enormous amount of energy. Matter is thrown outward in powerful jets and expanding clouds of debris. For a brief time, the explosion produces a brilliant flash of light, known as a kilonova. The energy released during this event can rival the brightness of an entire galaxy for a short period. But the merger is important for another reason as well. During the collision, conditions become so extreme that some of the heaviest elements in the universe are formed. Elements like gold, platinum, and uranium may be created in the intense nuclear reactions that occur as neutron-rich material is ejected into space. In this way, neutron star mergers help seed the universe with some of its rarest and most valuable elements. The golden jewelry on Earth may have originated in such collisions billions of years ago. For many years, scientists believed neutron star mergers must occur, but observing them directly was extremely difficult. Then, in 2017, something extraordinary happened. A pair of neutron stars located about 130 million light-years away spiraled together and merged. As they did so, detectors on Earth recorded the gravitational waves produced by the event. These signals were captured by observatories known as LIGO and Virgo, instruments designed to measure incredibly tiny distortions in space-time. For the first time, humanity directly detected the gravitational waves from a neutron star merger. But the story did not end there. Shortly afterward, telescopes around the world observed a flash of light from the same location in the sky. Astronomers had witnessed the same event using two entirely different methods. They had seen the collision both through gravitational waves and through light. This marked the beginning of a new era in astronomy, known as multi-messenger astronomy. By combining different forms of observation, scientists can learn far more about cosmic events than ever before. The discovery confirmed many predictions about neutron star mergers. It showed that these collisions do indeed produce kilonova explosions. It demonstrated that heavy elements can be formed during such events. And it provided new evidence supporting Einstein's theory of general relativity, all from the merger of two objects no larger than cities. After the collision, the fate of the merged object depends on how much mass it contains. In some cases, the combined mass may form an extremely massive neutron star, spinning rapidly and glowing brightly for a short time. In other cases, gravity may win completely. The merged object collapses into a black hole. If this happens, the final neutron star disappears behind an event horizon, leaving only the expanding cloud of debris behind. Either way, the merger marks the end of a long gravitational dance. Two neutron stars that may have orbited each other for billions of years finally come together in a single powerful moment. Far across the universe, these collisions continue to occur, invisible until their final moments. Silent spirals slowly tightening through time. Then, suddenly, an explosion of light and gravitational waves ripples across the cosmos. A brief, brilliant signal from two of the densest objects in existence. In the next part of our journey, we will explore what happens to the material thrown outward during these powerful mergers. Because within those expanding clouds of debris, new elements are forged atoms that may one day become part of planets, mountains, and even living beings. The quiet aftermath of neutron star collisions reveals yet another way the universe creates the building blocks of everything we see around us. When two neutron stars spiral together and finally collide, the universe briefly becomes a place of astonishing violence and creativity at the same time. The moment of impact releases an immense burst of energy. The collision shakes space-time itself, and vast clouds of neutron-rich matter are thrown outward into space at incredible speeds. For a short time, the explosion produces a brilliant flash of light known as a kilonova. The name kilonova comes from the idea that the event is roughly 1,000 times brighter than a typical nova. But the significance of a kilonova goes far beyond its brightness. Inside this explosion, some of the rarest and most valuable elements in the universe are created. To understand why this happens, we must remember the strange composition of neutron stars themselves. Unlike ordinary stars, neutron stars are made almost entirely of neutrons. When two of these objects collide, the debris thrown outward contains enormous quantities of neutron-rich material. In these extreme conditions, atomic nuclei can rapidly capture neutrons in a process known as the rapid neutron capture process, or simply the R process. This process allows elements to build themselves up extremely quickly. Atomic nuclei absorb neutrons again and again, growing heavier with each step. In just moments, atoms can become far heavier than iron. In fact, many of the heaviest elements in the periodic table are believed to form in exactly this way. Among these newly formed elements are gold, platinum, uranium, and many others. These elements cannot easily be created inside ordinary stars. Their formation requires environments where neutrons are incredibly abundant. and neutron star mergers provide exactly those conditions. When astronomers study the glowing debris of a kilonova, they detect signatures of these heavy elements forming in the expanding cloud. It is a remarkable thought. Some of the gold in rings and necklaces on Earth may have originated in such distant cosmic collisions billions of years ago, long before our solar system even existed. The explosion itself is both powerful and beautiful. As the neutron stars merge, the collision launches jets of material and expanding waves of debris outward in all directions. The expanding cloud glows brightly for several days or weeks. At first, the light may appear bluish and extremely energetic. Later, as the heavy elements absorb and re-emit radiation, the glow becomes redder and dimmer. This fading light provides astronomers with clues about the types of elements being created inside the explosion. By carefully studying the changing color of the kilonova, scientists can estimate how much heavy material was formed. In some cases, a single neutron star merger may create several times the mass of Earth in gold alone. For many years, astronomers suspected that neutron star mergers must be responsible for producing many of the universe's heavy elements. But the idea remained uncertain. Then came the historic event of 2017, when gravitational wave detectors recorded the inspiral and merger of two neutron stars. Shortly afterward, telescopes observed a kilonova explosion in the same region of the sky. For the first time, scientists were able to watch the birth of heavy elements almost in real time. The observations confirmed that neutron star collisions are indeed one of the primary factories for the universe's rare elements. In that moment, humanity witnessed the cosmic origin of materials that eventually become part of planets and sometimes part of ourselves. The expanding debris from a kilonova does not remain concentrated forever. Over time, the glowing cloud spreads outward into space. It mixes with the surrounding gas between the stars. Eventually, this enriched material becomes part of the interstellar medium, the vast clouds of gas and dust from which new stars and planetary systems form. Billions of years later, those elements may find their way into rocky planets like Earth, into mountains, oceans, and living creatures. The atoms created in a distant neutron star collision can become part of entirely new worlds. This connection between violent cosmic events and the material of everyday life is one of the most beautiful aspects of astronomy. The universe builds its elements through dramatic processes. Stars fuse lighter elements into heavier ones. Supernova explosions scatter those elements into space. And neutron star mergers create some of the heaviest atoms of all. Every part of the periodic table has its own cosmic story. And many of those stories involve the strange physics of neutron stars. Even though kilonova explosions are rare compared to ordinary supernovae, they are incredibly important. Each event contributes a large amount of heavy material to the galaxy. Over billions of years, these contributions accumulate, gradually enriching the galaxy with elements that did not exist when the first stars were born. In this way, neutron star mergers play a quiet but essential role in the chemical evolution of the universe. Far across the cosmos, these collisions continue to occur. Two neutron stars spiral together in silence for millions or billions of years. Then, in a single brilliant moment, they merge. A flash of light spreads through space. Gravitational waves ripple outward across the universe, and a cloud of newly forged elements begins its slow journey through the galaxy. In the next part of our journey, we will explore how neutron stars push the laws of physics to their limits. Because inside these tiny objects, gravity, density, and quantum mechanics combine in ways that challenge even our most advanced scientific theories. Neutron stars are not only fascinating because of their size or their density, they are also extraordinary because they allow scientists to explore the limits of physics itself. In most places in the universe, matter behaves in ways we can study easily. Atoms follow familiar rules. Gravity shapes planets and stars in predictable patterns. Time moves forward at a steady pace. But near a neutron star, many of these familiar rules begin to stretch. Gravity becomes so strong that space and time themselves begin to behave differently. Matter is squeezed so tightly that the particles inside atoms may rearrange into unfamiliar forms. In many ways, neutron stars act like natural laboratories where the universe performs experiments far beyond what humans can recreate on Earth. One of the most important ideas connected to neutron stars comes from Einstein's theory of general relativity. According to this theory, gravity is not simply a force pulling objects together. Instead, massive objects bend the fabric of space-time around them. Planets, stars, and galaxies all curve space-time in their own way. But the more massive and compact an object becomes, the more strongly it bends the surrounding space-time. Neutron stars are among the most extreme examples of this effect. Because their mass is concentrated in such a small region, the curvature of space-time near their surface becomes extremely intense. If you could place a beam of light near a neutron star, its path would bend dramatically as it traveled through the curved space surrounding the star. In some cases, light emitted from the surface can even curve around the star before escaping. This means that observers far away may be able to see more than half of the neutron star's surface at once. Space itself has been warped by gravity. Another remarkable consequence of this intense gravity is time dilation. Einstein's theory predicts that time passes more slowly in stronger gravitational fields. Near the surface of a neutron star, gravity is so powerful that time itself slows slightly. If you placed a clock on the surface of a neutron star and another identical clock far away in space, the clock on the neutron star would tick more slowly. The difference might seem small over short periods, but over long spans of time, the effect becomes noticeable. To an outside observer, processes occurring near the neutron star appear slightly slowed. In this way, neutron stars provide a real example of how gravity can influence the passage of time. Neutron stars also push the limits of how matter can behave under extreme pressure. Inside these stars, densities rise far beyond what exists anywhere else in the universe except perhaps inside black holes. Under such conditions, ordinary atomic structure cannot survive. Protons and electrons merge into neutrons, creating a sea of tightly packed particles. But even neutrons may not represent the final state of matter. Some scientists believe that at the very center of a neutron star, the pressure may become so intense that neutrons themselves begin to break apart. If that happens, their constituent particles called quarks could form a new type of matter. This hypothetical substance is sometimes known as quark matter. In such a state, the quarks that normally remain confined inside protons and neutrons might move more freely through the star's core. Another possibility proposed by physicists is something called strange matter. This exotic material would contain not only the familiar up and down quarks found in protons and neutrons, but also a third type, called a strange quark. Under the extreme pressures inside a neutron star, these strange quarks might become stable. If such matter exists, it could form the deepest core of the star. Some theories even suggest that entire neutron stars might transform into strange stars, objects composed almost entirely of this exotic substance. So far, these ideas remain theoretical, but neutron stars provide one of the few environments in the universe where such forms of matter could naturally exist. Another extreme feature of neutron stars is their surface gravity. The escape velocity, the speed needed to leave the star's gravitational pull, is incredibly high. On Earth, escape velocity is about 11 kilometers per second, but on a neutron star, escape velocity can reach nearly half the speed of light. This means that objects attempting to leave the surface must move incredibly fast to escape the star's gravity. Although neutron stars are not quite black holes, they come very close to that boundary. If a neutron star were compressed just a little further, its escape velocity would exceed the speed of light. At that point, it would collapse into a black hole. Neutron stars also allow scientists to test fundamental laws of physics in ways that cannot be done elsewhere. When neutron stars orbit each other in binary systems, their strong gravitational fields interact in complex ways. By measuring how their orbits change over time, astronomers can test predictions made by general relativity with remarkable precision. In some cases, these observations have confirmed Einstein's theory to extraordinary accuracy. The universe itself becomes the laboratory, and neutron stars become the instruments through which we explore the laws of nature. Despite their extreme physics, neutron stars remain quiet objects most of the time. They spin steadily. They emit faint radiation. They drift through the galaxy as the remnants of stars that once burned brightly. Yet within their tiny spheres of matter, the universe hides some of its most profound mysteries. How matter behaves under unimaginable pressure, how gravity shapes space and time, and how the fundamental particles of nature interact when pushed to their limits. In the next part of our journey, we will look toward the distant future of neutron stars, because even these incredibly dense objects cannot last forever. Over vast stretches of cosmic time, neutron stars slowly cool, spin down, and fade into the quiet darkness of the universe. Their story does not end with their birth, it continues for billions of years as they evolve into some of the most silent remnants of the cosmos. For all their incredible power and extreme physics, neutron stars do not remain the same forever. Like everything else in the universe, they slowly change with time. The story of a neutron star does not end with the explosion that created it. Instead, its life continues quietly for millions, billions, and perhaps even trillions of years. And during that time, the once fiery remnant of a massive star gradually cools and fades into the deep silence of space. When a neutron star is first born in the aftermath of a supernova, it is unimaginably hot. Temperatures inside the newborn star may reach trillions of degrees. For a short time, the star glows intensely in high-energy radiation. But neutron stars cool very quickly compared with ordinary stars. One reason for this rapid cooling is the enormous flood of neutrinos produced during their formation. Neutrinos are tiny, nearly massless particles that interact only weakly with matter. Because they rarely collide with anything, they can escape easily from the dense interior of the star. As they stream outward into space, they carry away enormous amounts of energy. In fact, during the first moments after a neutron star forms, most of its energy is lost through neutrinos rather than light. Within minutes, the temperature begins to fall dramatically. Over the next thousands of years, the neutron star continues cooling. The surface may still glow faintly in X-rays, but the intense heat of its birth gradually fades. As time passes, the neutron star also begins to slow its rotation. Many neutron stars spin rapidly when they first form. Some rotate dozens or even hundreds of times each second, but every rotation releases a tiny amount of energy. Radiation streams away into space. Magnetic fields interact with surrounding particles, and slowly, almost imperceptibly, the spin begins to slow. After millions of years, the once rapidly spinning pulsar may rotate only once every few seconds. After billions of years, its pulses may fade entirely. The star becomes quiet, no longer a cosmic lighthouse sweeping the galaxy with beams of radiation. Instead, it becomes a silent sphere of dense matter drifting through space. Yet in some situations, the life of a neutron star can take a very different path. If the star exists alone, its mass will remain nearly constant. But if it orbits another star in a binary system, gravity may pull gas from its companion. This material slowly falls onto the neutron star's surface. Over time, the neutron star becomes more massive. Normally, the dense neutron matter inside the star resists further compression. The pressure created by neutron degeneracy holds the star up against gravity, but there is a limit to how much mass this pressure can support. Astronomers estimate that if a neutron star grows beyond roughly 2 to 3 times the mass of the Sun, the internal pressure will no longer be enough. Gravity will take over completely. When this happens, the neutron star collapses once again. But this time, there is no force left that can stop the collapse. The star shrinks beyond the point where even light can escape. It becomes a black hole. This transformation marks the final stage in the life of the neutron star, a dense, city-sized object collapsing into something even more mysterious. A region of space where gravity becomes so strong that the universe itself seems to fold inward. Not all neutron stars will experience this fate. Many will remain stable for unimaginably long periods of time. But in the crowded environments of binary star systems, such transitions may occur from time to time. And when they do, the quiet remnant of a supernova disappears behind an event horizon. For most neutron stars, however, the future is much quieter. They simply cool and fade. Their surfaces gradually lose heat. Their magnetic fields weaken. Their rotation slows. After billions of years, the neutron star may become extremely cold and dark, almost invisible to distant observers. A tiny sphere of ultra-dense matter drifting silently through the galaxy. In the distant future of the universe, long after the brightest stars have burned out, neutron stars may become some of the last surviving remnants of stellar evolution. The cosmos itself will continue to change. Galaxies will slowly drift farther apart. Star formation will eventually decline. New stars will become rarer, but the compact remnants of earlier generations of stars, white dwarfs, neutron stars, and black holes may persist for unimaginably long spans of time. They will wander through the vast darkness of space, relics of a much brighter cosmic past. It is remarkable to think that these tiny objects, barely the size of a city, may outlive entire generations of stars. The neutron star that forms tonight somewhere in the galaxy may still exist billions of years from now. Long after our sun has completed its own life cycle, long after the night sky above Earth has changed beyond recognition, the neutron star will continue its quiet journey through the universe. A dense remnant of a star that once shone brightly, a silent witness to the passage of cosmic time. And so the life of a neutron star is both dramatic and peaceful. It begins with one of the most violent explosions in the universe, but it ends in quiet endurance. A tiny sphere of gravity and matter drifting through space for billions of years. A reminder that even the most powerful events in the cosmos eventually give way to calm. In the final moments of our journey tonight, we will reflect on what neutron stars reveal about the universe itself. Because these strange objects born from the death of stars help us understand the deep cycles of creation, transformation, and quiet persistence that shape the cosmos. As our journey tonight slowly comes to an end, we return to a quiet thought about the universe. Every neutron star we have explored began as something much larger. Once, it was a brilliant star shining across the darkness of space. For millions of years it burned brightly, creating light and warmth through the powerful fusion reactions inside its core. That star may have illuminated nearby planets, warmed distant clouds of gas, and quietly shaped the region of space around it. But eventually, like all stars, its fuel ran out. Gravity slowly took control. The core collapsed, and in a single powerful explosion, a supernova, the star ended its life in one of the most dramatic events in the universe. Yet the story did not truly end there, because from that explosion, something new remained behind. A neutron star, a tiny object only about the size of a city, and yet containing more mass than our Sunday, These strange remnants remind us that death in the universe is often also a form of creation. When massive stars explode, they scatter elements across space: carbon, oxygen, iron, and many other ingredients that eventually become part of planets, oceans, and living beings. Even the atoms in our own bodies were once formed inside ancient stars. In that sense, every supernova becomes part of a much larger cosmic cycle. Stars are born, they shine, they transform matter, and when they die, they leave behind the materials that allow new stars and worlds to form. Neutron stars themselves are also remarkable in another way. They act as cosmic laboratories, places where gravity, density, magnetism, and quantum physics reach their most extreme limits. Inside these tiny spheres of matter, particles behave in ways that scientists are still trying to understand. Superfluid neutrons swirl beneath solid crusts. Magnetic fields twist through space with unimaginable strength. Time itself slows slightly near the surface. In these distant objects, the universe reveals some of its deepest secrets. And yet, despite their extraordinary nature, neutron stars are also quiet. They drift through the galaxy in silence. Small, dense, enduring. So tonight, as you begin to drift towards sleep, you might imagine one of these stars far away in the darkness. A star that once shone brightly, now collapsed into a tiny sphere no larger than a city. A silent city of gravity floating through the Milky Way, its surface smooth and still, its interior filled with oceans of neutrons, its slow rotation continuing through the quiet night of the cosmos. And as your mind relaxes, you can imagine the universe continuing its vast, gentle cycles. Stars forming in distant nebulae, others collapsing into neutron stars, galaxies drifting slowly through the darkness, the cosmos expanding quietly in every direction. There is no rush, no urgency, only the slow and peaceful unfolding of time on a cosmic scale. Thank you for joining this calm journey through the strange and beautiful physics of neutron stars. Wherever you are in the world tonight, I hope these quiet stories of the universe have helped your thoughts slow down and drift gently toward rest. Now it is time to relax. Close your eyes, let your breathing become calm and steady, and imagine the distant stars shining softly above the earth. In a moment, gentle ambient music will begin to play. Let the music carry you into a peaceful and restful sleep. Good night, and sleep well.